In this module, we will consider sound waves. Sound waves are a familiar example of longitudinal waves. Molecules in the air oscillate in the direction in which the sound wave is traveling. As a group of air molecules moves forward, they approach the molecules ahead of them, creating a region of higher density and pressure, something called compression. Behind them, they leave a region of lower density and pressure called rarefaction. The pressure gradient creates a restoring force on the displaced air molecules, but also perturbs neighboring regions of air, causing the wave to propagate. We can describe the wave either in terms of the displacement of the molecules or in terms of the change in the pressure of the air away from its equilibrium value. In either description, the wave travels with the same speed. The volume of a given group of air molecules changes due to the oscillations, and the pressure in that volume changes. Now, it is the bulk modulus which relates changes in the volume of an object to the change in the pressure acting on it. So it is not surprising that we find that the speed of propagation of waves in air is equal to the square root of the bulk modulus divided by the density of the air. We can visualize the waves in terms of the density of the air molecules. The highest densities are shown as the darker shades and the lowest densities as the lightest shades, and here we illustrate a wave traveling towards the right. If we wish, we can describe the sound waves in terms of the change in the pressure away from equilibrium. If the sound waves are sinusoidal, then we can describe them as the sine of kx minus omega t times delta p max, where delta p max is the maximum change in the pressure away from ambient pressure. We can also describe the waves in terms of displacement of the air molecules away from equilibrium. In this case, the waves are described by cosine kx minus omega t times the amplitude, which is the maximum displacement of the particles in distance away from equilibrium. Notice that there is a 90-degree phase difference between these two wave descriptions. To understand this phase difference, notice that the green shaded region is a region where all of the particles have a positive displacement. That is, they're moving towards the right or towards a region where the density and pressure are at their maximum. The yellow shaded region is a region where all the particles are moving to the left. They have a negative displacement and are moving again toward the region of highest density and pressure. And in both cases, they're moving away from the region of the lowest density and lowest pressure. Now, these two descriptions of the waves are related to each other by a relationship between the maximum pressure and the maximum displacement. Each element of a sinusoidal wave behaves like a simple harmonic oscillator. A useful expression for the energy in an infinitesimal bit of mass dm in a sound wave is that the infinitesimal energy is 1/2 the infinitesimal mass times the square of the angular frequency of the waves times the square of the amplitude of the waves. Now, because sound waves travel in a real medium, not in an ideal one-dimensional string, we need to think about how much wave energy is passing through an imaginary cross-sectional area A. The amount of mass, dm, that's passing through this cross-sectional area A is the density of the air times A times dx, which is an infinitesimal thickness in the direction of the velocity. And we can substitute this in for the energy. Now, this means that the rate at which energy is carried through the cross-sectional area A is given by the power, which is dE dt. And we see that in our expression, the infinitesimal distance d has now become the velocity of the wave. More relevant is the intensity I of the sound waves, which is the energy per second per unit area carried by the sound waves. We can also relate this intensity to either the maximum displacement, S, or the maximum pressure, delta P. Sound level, often referred to as loudness, is a measure of the intensity of sound waves. Because humans can detect loudness over a vast range of intensities, sound levels are usually measured on a logarithmic scale. Here, beta gives the decibel level for a given measured sound level. In this equation, I0 refers to the threshold of hearing, which occurs at a level of about 10 to the minus 12 watts per square meter, which corresponds to 0 decibels. Sound becomes dangerously loud at about 120 decibels. We can also invert the equation for sound levels to give the intensity as a function of the sound level in terms of decibels. Of course, the intensity of sound waves frequently depends on how far we are from the source of a given sound. The reason is that energy is conserved as sound waves travel, but the waves typically get spread over a larger area as they get farther from the source. For a point source of sound, the energy is spread over the surface of a sphere, so the intensity, which goes as the power divided by the area, is going to be given by the power divided by the surface area of the sphere, which depends on radius as 4 pi r squared. Since the intensity falls off as 1 over r squared for spherical waves, the amplitude of the spherical wave's oscillations fall off as 1 over r.